Review for the test. Okay, put this in and you're good to go. I always forget about this part. There we go. And don't leave without me passing back my stack of stuff today. Lots to pass back. Okay, chapter 25, the last chapter. Yay. This is probably one of my more favorite chapters. So here we're going to assume that we're talking about a field. F is going to represent a field. It says every ideal of f of x is principal. They go through the proof of that. It's actually rather short. What is the hypothesis for this one? This is on page 251 if you're following along.
J be an ideal of f.
So J be an ideal of f of x. Then they break it up into two parts, right? Either J has only 0 in it, or J has other non-zero terms. So the first case we're going to have is that J only contains the 0 element. So that would be our 0 polynomial. But if J contains a 0 polynomial, then what happens? How can you write J? Yeah. J is equal to 0, which is principal. So the second case, J has a non-zero element.
Principal ideal just means the Phillips products and
That's a generator.
What is it?
Yeah, a principal ideal means that it has a generator. Okay, so how do we assume that there's some A, did they call it A? They called it. Okay, so then they define a B. What do they define B to be in this one?
Polynomial of lowest degree.
Yeah, B of x, be the polynomial. Be a non-zero polynomial of least degree, right? To be okay. So, by the way, how can we assume that there is a non-zero polynomial of least degree? What allows you to make that assumption?
because you're in a space where you're trying to show that B is your generator, right? So that
Yep.
means
There's a well
Well-ordering principle.
so every power of that.
Every power of that is in there. Yep. So this is follows by the well-ordering property. Okay, then what do they do with B?
Now, sorry, real quick. When we were talking about only being an ideal here. Ideals, but F is a
So it doesn't have divisors of 0. Mhm.
But J is a subset of that.
J is a subset of F, therefore has no divisors of 0. Mhm. So apply the division algorithm, right?
Our goal being to show that J is generated by B.
Mm-hmm. Yeah, goal is to show J is generated by B.
And they define an A that's also in J, just some polynomial in J.
Okay, so apply the division algorithm. So we're just going to have A is going to be something in J.
You do the algorithm, you're right.
So the division algorithm says what? There exists, what did they call it in the book? Q and, well, don't we need a Q and an R? Yeah. And what properties do we know about A of X? A of X is equal to B of X, Q of X plus R of X. And what do we know about R?
The degree is less than or equal. No, sorry, less than.
Yeah, degree is less than degree of B of X, or R of X is equal to the 0 polynomial, right? Okay, so those are the things that we know. How does this help us?
It's with R of X is 0.
Yeah,
So that's not.
so assume R of X is not equal to 0. Then you know that the degree of R of X,
And less than the degree of B of X,
yeah,
but B of X is the polynomial.
mhm. So that tells us R of X is not in J, right? Because its degree is too small to be in J, if it's non-zero. Then what?
Therefore, it's a contradiction. So
Why is it a contradiction?
because you created a function R of X that is of less degree than B. So
Oh, because we stated that our
Should have done the R equals 0.
R, in other words, R of X equals 0 is in our idea.
does R of X have to be an F of X?
Yes, that's what I need to hear. Does R of X need to be an F of X? Notice I was very careful. I just said it was an F of X up here. Does it need to be in J?
Yes, because A is.
Yeah, but the division algorithm doesn't necessarily tell you that R and Q are in J. How do you know that R and Q have to be? You know A is in J.
Because E is in J.
Yeah, but you back
Yes, yes, right there. So let's put that in right here. Note that A of X is in J. A of X and B of X are in J.
Because it's not good. It's not product here.
Yeah, what we're going to do is we're going to say R of X, which is equal to A of X minus B of X, Q of X. Ideals are closed under subtraction. They contain their products, absorb their products. So this has to also be in J. So now we have our contradiction. So what is the conclusion then? only problem we had was when r of x was not equal to 0. Uh-huh. Which is like Jimmy was saying, we should do that case second instead of first. So let's take this out here and move it down. So that allows us to conclude.
Okay, do we know that Q is in J, or, okay,
You don't need to know
So-
Q is in J, it just absorbs its product.
why does A of X equals B of X, Q of X tell you that B of X is the generator? Because for a generator, wouldn't we have some constant number
It's a
operating on B of
constant,
X?
it's a constant form.
It's a generator, it's not the generator.
But I mean, like, being a generator, doesn't that mean that by operating with yourself X number of times,
Operating,
you can
to
get,
generate it. What we were
But if
doing,
it's of the least degree, it has to be the generator. doesn't
you can have it differences of the leading coefficient. Yeah.
my question is how we get from
It's-
E there to 6, to the conclusion. Because like when we first started dealing with generators, it's like A to the N is equal to everything, we'll give you every element.
Yeah. And you just repeat the process with B. So yeah, I suppose we should put in a little bit more. You're gonna repeat the process with Q and B.
But we don't know that Q is in J, do we?
I see what you're saying.
A is any element of J. B multiplies anything, makes any element. Therefore, it generates any element.
Yeah, like you can make any element out of it.
Yeah,
This Q is
but-
arbitrary.
When we're saying principle, we usually use itself operating on itself
Generator.
to generate something, but maybe that definition doesn't work here.
Wait a minute, when you say, you're saying principal generator is like saying B squared, B cubed, B
The
whatever?
definition down here. Yeah.
I mean, that's the definition of generator that we used before.
Oh, but when we were in rings, when we were in groups, we were using multiples instead of power. So A, 2A, 3A. I think they're just using multiples. You find the generator.
But this isn't really, I mean, multiples are still just B plus B plus B plus B.
Well, no, multiples using multiple elements in it. So in other words, if you said multiples of A in some ring, some group A, then it would be A operated on by other elements of A.
The multiples are just like, if you have some group A, some ring A, and multiples.
Oh,
like
I know what
5A.
yeah, that's coming from when we're living in the integers. But when you're not living in the integers, then you get to multiply by other elements in your ring.
Okay. I thought multiples were just the additive version of exponents.
It is if you're talking about our exponential workup that we were doing, but if you're talking about two elements multiplied together, then they both come from the group. But remember when we were dealing with the integers, we were showing that the integers were the only ring that had those properties that we were talking about. And you're getting that one confused with n dotted with 1 or n dotted with a, where you're doing integer multiples of it. When we first started and defined multiples, we were defining them based on the set that you're in. So it's that value times any value in this set gives you the multiple instead of the integers, instead of operating on itself.
Okay, so it's just a different definition of multiple.
Yeah, it's
So this
kind of the
feels more
context.
like multiplication.
Yeah, this is dealing with multiplication of two polynomials together. it all depends on what you're talking about for your ideal. And we had been talking about in the last 3 or 4 chapters just the integers. And so we were raising them to powers because you can generate any integer from one.
Okay.
Yeah. So that's the difference. That's a very good question, though. I hadn't actually thought of it. Let's see. That's the end of that proof. What is a possible generator for your ideals, for your principal ideals in these polynomial fields? This is the conversation we had, sort of, in amongst the conversation we're having with Isaac.
So
It's a polynomial of least degree, but is it a specific polynomial or there's a whole bunch of them
has to be
around?
an arbitrary coefficient.
Yeah, the coefficients can change over it. Because if you take 2 polynomials and you multiply them together, if you divide one of them, the leading coefficient out, then you just have to multiply that into the second polynomial so that you have your same answer when you're done multiplying it. So you can change your leading coefficients. So it's a number of polynomials, but it's a polynomial, it's any polynomial of least degree.
That degree is still positive, right? 'Cause it can't
Positive,
be a
yeah.
constant.
Yeah, because if you have a constant polynomial, you can't generate your higher powered terms. Okay, so let's continue.
Which is kind of weird to me because if you're in a field, right, and J is a subset, then what would happen if you took your polynomial of least degree and divided it by itself? It wouldn't contain,
Any polynomial divided by itself should be equal to 1.
yeah, but that wouldn't be in the same set.
We're not talking division, we're talking multiplication.
That's a field, it doesn't matter.
Oh, the f of x, no one said that f of x was a field. In other words, the inverses of
Oh,
polynomials
just
don't
just the
necessarily
just the
exist.
coefficients.
Yeah, just the coefficients
Yeah.
form a
Okay,
field.
sorry.
Yeah.
Polynomial stuff is usually not gonna be a field because inverse polynomials are not nice.
Exactly.
Okay.
Very similarly to why you can't divide by matrices.
Well, it works with polynomials.
Yeah, you can do polynomial division, but you don't have the inverse doesn't live in the set of polynomials because you're going to have negative coefficients, negative exponents, sorry.
It was not with polynomials, a natural number.
Yeah. Okay, so let A and B be in our polynomial field where f is a field, our polynomial ring where f is a field. We say that b of x is a multiple of a of x if b of x equals to a of x times s of x, and where s of x is an f. And if b of x is a multiple of a, we also say that a is a factor of b, or that a divides b. In symbols, you can write that with a vertical line or division, divides. Notice whenever we use the term divides, we're not talking about fractions, because when you write it as a fraction, then you must go forth and prove that it actually is an integer and not a rational number with decimals or something like that.
We do it
So,
with multiplication.
Yeah, we always use the multiplication definition. Yep. Every non-zero constant polynomial divides every polynomial. Why?
Because we just distribute everything.
Mm-hmm. Yeah, and we're in an integral domain, which means that you have no divisors of 0. So everything has a multiplicative inverse in f. It's a field. So you can actually go through and factor out that leading coefficient and divide by it. The invertible elements of your field f of x are all the non-zero constant polynomials. They're the only ones that you can write as an inverse in your field. So there are some terms that are invertible in the polynomial ring, but not all of them. A pair of non-zero polynomials, a and b, are called associates if a divides b and b divides a. What does that tell you? If both a divides b and b divides a, what does that tell you? B. They're constant multiples of each other. Mhm. So associates simply means they're constant multiples.
It's kind of like absorbent, right?
Well,
not
absorbing,
exactly.
yeah, not exactly. It just means that they look the same other than what their leading coefficients are. So in our polynomial ring, if A and B are associates, A and B are associates if and only if they're constant multiples of each other. This was a very short one, so I figured, well, we can outline it. What's the hypothesis?
A of X and A of B would be enough.
Yeah.
And it would be associated.
You're waking Christina.
No.
No, she just made me make sure.
Oh, okay.
I do that when I feel like I'm falling.
Yeah, unfortunately, then you wake up and you're wide awake for the next.
Yep, I'm
Yep.
just like, fight or flight, fight or flight.
Assuming A and
It's
B
like,
are
fall or
associates.
flight.
Yeah. Assume A and B are associates. Apply the definition. You're going to have A of X is equal to B of X times Q of X, and B of X is equal to A of X times R of X for some Q and R. And then what did they do? They did substitution, right? I forget which one they substituted for, but we're going to substitute for B of X. So that's going to be equal to A of X, R of X, Q of X. But then what does that tell you?
That R of X, Q of X is equal to 1.
Yeah, they forgot to show the step for how they did it. So let's actually put this in.
They do it all the time.
And then you factor. And then what does that tell you? Since there are no divisors of 0,
So 1 of those is equal to 0.
either A of X is equal to 0 or 1 minus Q of X R of X is equal to 0. But the assumption was that A of X was not equal to 0.
Where does that assume? Should that be in the lemma?
That should be up here in the lemma. I think that's actually in,
This is not one. There is non-zero point.
yeah, right there. Oh, that's in the definition
Yeah,
of
it's
associates.
associates, okay.
Well, it's in by the definition of associates. So it should be right down here. Apply the definition of associates. A of X and B of X are not equal to 0. So, since A of X is not equal to 0, then you know 1 minus R of X Q of X is equal to 0, which tells you that 1 is equal to R of X Q of X. So what does that tell you about R and Q? They have to be constant polynomials, right?
Exactly what it is.
Yep.
Question.
Yeah.
Do we know that we're in the integral domain right now?
Yeah,
Can
because
we
F
just
is a field.
Can we just use cancellation? Or can we not do that because we're doing a polynomial, so we can't use say?
We don't know what A inverse is. Yeah. It may or may not
Don't all integral
exist.
domains have the cancellation property?
We're using the idea from an integral domain that has no divisors of 0. It's kind of interchangeable because we have shown that those two properties exist, but we are steering clear of saying A inverse exists, because if you think about polynomials, you have to define where the inverse specifically exists at. Okay, so they have to be constant polynomials since these are the only invertible polynomials. That we know of in f of x.
Except,
I mean, there could be others, but these are the only known invertible polynomials, already known.
they're always in front pairs,
Yeah,
so there could be an infinite number of them.
well, there will be an infinite number of them, assuming that f is infinite and not finite.
Yeah.
That tells us that A of X is a constant multiple of B of X.
Mm-hmm.
And similarly.
Yeah, are constant multiples of each other. Which is exactly what we were trying to show. That's one way. Now, going back the other way, is it any different?
No.
No. This actually goes both directions. So we don't have to rewrite it. If we're writing it, we'd have to use if and only if arrows throughout here. So
This
we'll
is
just
a
say,
really random question, but how many proofs out there do you think?
how many proofs are there out there?
How many proofs out there do you think that go only one direction, they don't go the backwards direction, but they actually could be reversible? It's obviously if only if it's a stronger case.
Most of the time, people think about the only if part, even if they don't prove it. So I would say it's less frequent than you would expect.
Hey, Dr. Anderson,
Yeah.
can you just say something about, like, wait, in number 5, you said R of X and Q of X are constant polynomials, and C is the only known invertible polynomial in F of X. Is that just,
We don't know what the inverse of a general polynomial is in f of x, because we don't know anything about f other than it's a field.
okay.
So, but you know that you can find for each constant, you know, you can find the inverse of it because f is a field. So those are the ones that we know the inverses exist. Now, just like x cubed in the real numbers has an inverse, but x squared does not over the entire reals.
Okay.
That's what we're running into our problems here. We don't know which of those non-constant polynomials actually have the inverses on the field of definition. And even more so, we haven't specified what we're plugging in for x yet. It's just a placeholder.
Okay.
Okay, so more definition. Any polynomial whose leading coefficient is 1 is called a monic polynomial. And every non-zero polynomial has a unique monic associate. That just makes so much complete sense. We're not going to worry about the proof of that. You just,
Constant
yeah,
multiple multiplied by 1 over whatever, the inverse of whatever.
exactly. And because multiplication of two known numbers is unique, it forces it to be unique. Then where we're headed today, greatest common divisor, because of course we are going to find greatest common divisors of polynomials. Yay. A polynomial d of x is called a greatest common divisor of a of x and b of x if d divides a and d divides b. And for any u and f, if u divides a and u divides b, then u has to divide d. That's kind of our way of saying d is bigger than any of the others that divides it. So that's our definition. We are going to select the monic polynomial from the set of associates of d of x and call that the greatest common divisor. So we're going to choose the monic one, which allows us then to view the greatest common divisor as a unique polynomial. So on your homework, please choose the monic.
If this, why, if it's the greatest common, why must it be monic? Why couldn't it be quadratic or other things?
Monic doesn't mean not quadratic. It means that the leading coefficient is 1.
It's like just a standard form.
Yeah. You didn't say it right.
Why not like choose something like 9?
Well, just because we want to be able to say the greatest common divisor is unique. And the only unique divisor would be the monic.
When you say from the set of associates, does that just mean like,
All constant multiples.
okay,
So if something is a greatest common divisor, then any constant multiple of it also is a greatest common divisor. Well, choose the only unique one out of the set, and that would be the monic. Now, you could have specified any leading coefficient as the one you want to choose. But we just chose 1 for the leading coefficient.
okay,
So our division algorithm, it says any two non-zero polynomials, a and b and f of x, have a greatest common divisor. And furthermore, the greatest common divisor can be expressed as a linear combination. So let's actually prove this one. Well, outline it. What's the hypothesis?
You have two non-zero polynomials.
I think this it follows pretty much exactly the same way as the
Yes, it does.
this is the second theorem in the book, right?
Second. Theorem 2.
So it's 23.
Yeah, and we're going to be mimicking that proof. So what we need to do is we have to show a greatest common divisor exists. And then we have to show that it's a linear combination. So there's 2 things to do. What do they do? They had a trick in the theorem. What was their trick? They defined an ideal.
The only difference between this and the regular is that because we use R of X for this, it's a plus items. We expanded that into functions. That's X and P of X. So this is there's not an R of X.
Oh, R of X. Oh, for the division, yeah. We're getting to that. We're not there yet. We're going to get there. So they define J to be all the linear combinations of A and B. And this is where U of X and V of X are in F of X. Yeah, in fact, I'm going to write this a little bit. We like set notation, set builder notation, right? It makes things so much smaller. Okay, so there's our J. Then what?
You find that A and B are in their house.
Yeah, they claim J is an ideal. Why is J an ideal?
Because
You take anything.
U of X or AX.
anything that you multiply, like if you multiply some other polynomial by that, you can just fold that in with the u and the v, since u and v come from f.
Mm-hmm. So let's just put it, it's closed under multiplication. Since
You want closed under multiplication. absorbs products.
absorbs products is a term we use. So if we're going to have anything in here times, I don't know, a w of x would be equal to u of x, w of x, a of x, right? Plus v of x, w of x, v of x, which is in j. And close under subtraction. So if you subtract two of them, we need, this is going to be some u1 and some v1 minus some u2, v2. But what happens?
Terms and subtraction,
Yeah.
factor out the a's and b's.
So then v1 minus v2, v of x, which is in j. So j is an ideal. That was one sentence. And then they write it as generated by d of x. Why? Isn't that our first thing we did? Every ideal of f of x is principal.
Mhm.
No. So you know that everything in J is a multiple of D. What do you know about A and B? Has to be in J. Why?
Because a is 1a plus 0b.
Yeah. Since A of x is equal to, we'll put it this way, 1x plus 0 b of x. And b of x is equal to 0 a of x plus 1 b of x. So then this is where they combine them together. I know a of x has to be equal to d of x. What do they call it? Oh, they just do d divides. We get d of x divides a of x, and d of x divides b of x. Now, if d divides a and d divides b, we're going to get a common divisor and show that that common divisor has to divide d of x. What special property? Well, we'll just go with here. So let k of x be an f. Such that k of x divides a of x and k of x divides b of x. What does that tell you? Yeah, we know f of x and g of x and f. I know that, which one goes with which? A of x is kf. And b of x is k times g. I missed an equal sign in there. Now, how does that help?
Now everything is in terms of K, so we can substitute back
Mm-hmm.
and show that it's
Yeah, but we know d of x was in J, right?
Yeah.
And so we need one other step. I should
So
put
we
this
can
in.
write d of x as a linear combination of a and b, and then
Yeah.
we can substitute in our values for a and b. Or
So I'm gonna do that right here. And what did they call that for d of x? R of x. X plus s of x, b of x. And so we're gonna substitute. And let me label this.
it does that automatically.
Yeah, it does, but I'm not actually compiling it, so I mean, I will compile it later, but I want to see it right now for you guys to know what it is. So, by substitution of, and this is going to be 2. I want one, yeah, equation 2 into equation 1. You're going to have d of x is equal to r of x, but a is k of x, f of x, and b of x is k of x, q of x. But then, what can you factor out?
D of x?
Okay. Yeah, that's just.
That's g, yes, can't read. So factor out k of x, and you're going to have r of x, f of x, plus s of x, g of x.
Because it's easier, right?
We've been commutative for many chapters now, but yeah, commutative. You have to know that. So what does that tell you?
that a divides g.
No, it isn't.
But actually, it's a field. That's pretty much.
Commutative ring with identity having the
All
no
non-
divisors is 0 and every non-zero element is multiplicative inverse. That's a
Do
field.
fields have- Our fields require,
Yeah.
the fields explicitly have the no divisor of 0.
Yeah, because every non-zero element is a multiplicative inverse.
Yeah. Therefore, it has to be.
Yeah. So d of x is the greatest common divisor.
The other thing you can think about is that it wasn't.
To actually find the GCD of two polynomials, do we do Euler's or Euclid's process or whatever for GCDs? We divide it evenly.
Yep.
and how do you come up with the linear combination once you've done that?
I'm going to show you how to do that. That's exactly where we're headed. Okay, we have some other definitions and theorems, but we are actually not going to prove those theorems. The definitions are two polynomials are relatively prime if their greatest common divisor is 1, the constant polynomial 1, and A is said to be reducible if there are two other polynomials, so that A is a multiple of those two other polynomials. In other words, you can reduce it if you can factor it. So, and the degrees of C is less than the A and the degree of B is less than A. So you're factoring it into two non-constant polynomials. A polynomial P of positive degree is said to be irreducible if it cannot be expressed as a product of two polynomials of positive degree. Notice we didn't call it prime, we just said it's irreducible, but it's kind of indicative of our prime numbers. Okay, the polynomial x squared plus 1 is irreducible over the reals, but it is reducible over the complex numbers. Why? You can't factor x squared plus 1 in the reals. but you can factor it in the complex numbers. It's x plus I, x minus I. So that's why. Euclid's lemma for polynomials, it says let p of x be irreducible. If p of x divides a times b, then p divides a or p divides b. That's Euclid's lemma. The corollaries after that, let p of x be irreducible. Then if p divides the product of n polynomials, p has to divide one of those n polynomials, at least one of them. It could divide all of them, but it has to divide at least one of them. And then the next theorem, if q1 to qr and p are monic irreducible polynomials, if p divides q1 to qr, then p is equal to one of the factors because they're all monic, they're all irreducible. So saying that p divides one of them is the same thing as saying that p has to equal it because we have divided off the leading coefficient. There's only a unique polynomial there.
You're saying that p of x is equal to q sub 1 of x.
Or q sub I for some I.
Or, yeah, okay.
It's one of them. But that's just because we assumed monic and irreducible.
Really quick.
Yeah.
This is just a interesting thing. If you were in a complex plane and you wanted to look at those particular polynomials, like C of X,
Mm-hmm.
when you, the coefficients can be imaginary.
Mhm.
Right? So you have, technically speaking, two terms. You can have two terms that are the same degree.
Yeah, because you have the imaginary and the real part. But we kind of view that as just one complex number.
Yeah, that's true.
But that's why when we go to graphing complex equations, we graph them. One complex number has to be graphed in 2 dimensions.
And then
So
you-
if you have a 2-dimensional function, you got 4 dimensions.
Yeah, exactly.
You have problems.
Just,
And so we just don't graph them that much. I mean, you get surfaces and stuff like that. It becomes hairy. Unless you're graphing paths or something like that, which would be a vector. Yeah. Okay. Every polynomial of positive degree in f of x can be written as a product k, p1, p2 to pr, where k is constant and the p1 to pr are monic irreducible polynomials. I was going to prove that, but we're not going to prove it. We're going to go and look at our example. By the way, if you can, theorem, the last term here is showing this is uniqueness. And this is a very cool, slick argument that they do. They say if A is equal to one product and another product right here, and the P1s to PRs and Q1s to Q1s are all monic irreducible, then you have just the constants, the K and the L. And so you can divide those because we know that those inverses exist, so you can multiply by those inverses. And then you know that P1 has to divide Q1 to Q1, so it has to be equal to one of those. Then you know P2 has to divide what's left, and you know P3 has to divide what's left, and so on. And so it's kind of an inductive argument with a finite number of steps. So it's a very cute little proof on it. It's a very short little proof, actually.
we technically assume that all the time. Right?
Yes.
We look at, oh, we have X squared over here, X squared over here.
Yeah.
It must be-
They must be equal, cancel. And in fact, when we do the partial fraction decomposition, that's exactly what we're doing.
Mhm.
But it's a lot of fun trying to get calculus students to wrap their minds around what's actually happening for partial fraction decomposition. It takes a little bit. It's not
Yeah,
immediate.
Using one equation to solve.
Yes, exactly. Okay, so how do we do this? Find the greatest common divisor of x to the 24 minus 1 and x to the 15 minus 1. So we have to actually go do our division. Let's divide x to the 24 minus 1 divided by, let's see if let's see if let's divide.
We're allowed to use a calculator and calculate some type of program for these problems.
Yes, scientific workplace can do it. But what you need to do is you have to write this using kind of the division algorithm. So you need to know, what does that tell you? That means that x to the 24 minus 1 is equal to x to the 15 minus 1 times what? Times x to the 9. And then what's your remainder is going to be x to the 9 minus 1. You have to keep that. And then that's our calculation right there. Now we're going to repeat our calculation, but now we're going to do it with x to the 15 minus 1 and x to the 9 minus 1. Yeah, there's not too many steps. Compute, polynomials, divide. So then I'm going to write this as x to the 15 minus 1 is equal to x to the 9 minus 1 times x to the 6 plus, and then we're going to repeat this again. This becomes 9 right here, and this becomes 6. And we delete that, and we compute polynomial divide. And so then that tells
Why
us
is x is 6?
you always do it with the two polynomials, the one that you divided by and the remainder. So you're going to have x to the 9 minus 1 is equal to x to the 6 minus 1 times x cubed plus, yeah, and so repeat. So this becomes an x to the 6, and this becomes an x cubed. Polynomials divide. So then that becomes x cubed plus 1. So we have x to the 6th minus 1 is equal to x cubed minus 1 times plus 0. When you get to plus 0 right here, yeah, that is a difference of 2 squares. When you get to plus 0 right here, you know that the previous polynomial on the end, if you've written it in this form, the previous polynomial is the greatest common divisor. And we want to choose the monic. So if this wasn't the monic, you would factor out the leading coefficient and give me what's left inside. So in this case, this is going to be x cubed minus 1. I'm going to just write a GCD of x to the 24 minus 1 and x to the 15 minus 1.
How did you know that?
This is always, when you're doing Euclid's algorithm, which is what I'm doing to find the greatest common divisor, the non-zero remainder is the greatest common divisor.
Okay.
And you can write it as a linear combination.
I never thought of it this way, but this is exactly this regular division algorithm. It's just written in the form. You're just implicitly subtracting each of these remainders over and over.
Yep. So you're keeping by factoring into the remainder.
Now,
Which is actually a way to prove the division algorithm. I've actually proved it that way. Depends on which way the book does it, but there's many textbooks that prove the division algorithm that very way.
okay. How do we know, like you have the grace of the computer here that tells you hopefully like roughly what you have.
On a test that we have.
No, I'm going to give you very simple polynomials. You will be able to divide them very quickly, and they'll be like 2 steps. Yeah, it will not be
I'm
long.
just thinking like, I don't know that it was class one.
No, we do the hard ones on the homework. Okay, so that I say this before I do that, when you're trying to write this as a linear combination, You solve this last step for the x cubed minus 1. So you're going to take this over to the previous one. And you're going to work your way backwards. Back substituting, yeah. So x cubed minus 1 is equal to x to the 9th. Oops, I didn't want that there. We want it right here. Is equal to x to the 9th minus 1 minus x to the 6th minus 1. And then outside, that's going to be an x cubed. Now, from this one, you know what x to the 6th minus 1 is equal to. So you're going to plug that in here for x to the 6th minus 1. So our x to the 9th minus 1, yeah, this part, this is where you want a computational engine. So x to the 6th minus 1 is equal to x to the 15th minus 1 minus x to the 9th minus 1 times x to the 6th. And let's put all of that in brackets. I'm going to simplify on this step right here because I have an x to the 9th minus 1 and there's another x to the 9th minus 1, but it's times that x cubed. So,
Or there's another x to the 6th.
So
Yep.
x to the 9th plus 1.
well, no, don't lose the x to the 9th minus 1. We're going to need that.
But it's x to the 9th plus 1 times x to the 9th minus 1.
You're simplifying too far.
Let's start.
Yeah, that x to the 6th and x to the 4th.
Yeah, you have x to the 6th and x to the 3rd multiplying it. So it's going to be times 1 plus, oh, I see what you're doing. X to the, no, you're doing just fine.
Okay.
I thought you were actually multiplying this out somehow in your head. Okay, and then you have a minus x cubed, and you have x to the 15th minus 1 times the x cubed, right? Now, we want to keep this x to the 15th minus 1, but we want x to the 24th minus 1 showing up in there. So we solve this one for x to the 9th minus 1, and we replace it right here. So that's going to be x to the 24th minus 1 minus x to the 15th minus 1 times x to the 9th. And now all of that goes in those brackets. And that's times 1 plus x to the 9th. I'm going to write that as x to the 9th plus 1. And then minus, and this just comes down. Now, this has x to the 15th in it, so we have to combine it with that one. And then we'll be done. So we have x to the 24th minus 1 times this x to the 9th plus 1. Right? It's just that times that. And then we have minus x to the 15th minus 1 times from,
It's
yeah,
x to the 9th times x to the 9th plus 1 plus x to the 3rd. Plus.
is it plus? Yeah.
Yeah. So like,
And we're not going to simplify beyond that.
That's simple.
This is simplified because this is a polynomial.
well, can you just rewrite that as x to the 18 plus?
Okay, if you want it simplified.
Well, I guess there's no point in that. Never mind.
You can if you want.
Let's just watch it really.
Or you can
That's
turn it
okay.
around.
So this is x to the 18.
You really want to get
Why don't you just let place it?
Because it will simplify
All right, let's
everything
simplify
out.
down to x cubed minus 1.
It will get back to where you started, and that's where you want to go.
Hey, it worked! Yay!
Yay!
X cubed minus 1 equals x cubed minus 1.
That's what you want it to equal. It'll actually try and solve the equation because you have a Or if you take it out on the line by
But that's
itself.
as far as we wanna go.
That's
isn't
as
it?
far as you want to go. This is some polynomial. You want it in something with your beginning two polynomials. So you actually are doing that on a homework problem. I think
Oh, wait,
you have
wait.
one.
Won't it be like x to the third times, x to the third plus 1 squared?
No, we don't need to factor that anymore. You can if you want, but you don't have to.
I was thinking it was gonna end up being x to the 9 plus 1,
No. And then on your homework, in your homework in Z5, they give you this polynomial, 2x cubed plus 4x plus 1. You need to know that the 0 that you would normally put in for the x squared term, you're going to call it a 5 instead of a 0.
Well, we just write that down really quick.
Yeah. This is going to be for A5. And after you do some simplification, you're going to end up with a 2x plus 1. Go ahead and write that as a 2x plus 6, because then you'll be able to see how to finish it. So here again, you're
What
just
is this
adding
in?
5. This is in Z5.
Five.
Yeah. So those are the hints that you're going to need for your A5 homework problem. It's kind of fun if you know those two hints. Anyway, we're done for today. Let's see.